Welcome to today's Explainer, where we're going under the hood of aircraft instruments. As an aspiring pilot or just a hardcore aviation enthusiast, you already know that flying is so much more than just looking out the window, right? It's about deeply understanding the literal machines that guide us. Today, we're going to dive right into the inner workings of the systems you'd find in a Cessna 172S or Piper Arrow. Let's get into it. So, imagine you're flying directly into a massive, thick layer of clouds. You can't see the ground below you, you can't see the sky above, your eyes literally cannot find the natural horizon. How on earth do you keep the airplane right side up? Well, understanding your instruments isn't just some boring regulatory requirement, it is an absolute lifeline when your own eyes start playing tricks on you.
Here's our flight plan for this explainer. We'll start with modern glass cockpits, then move into the vacuum system, touch on gyroscopic physics, look at the flight instruments themselves, break down compass errors, and finally wrap up with time turns.
All right, part one, modern glass cockpits. You know, modern planes use these incredible digital attitude and heading reference systems. We call them AHRS for short. They use rate sensors and accelerometers to give you flight data, honestly, very much like how your iPhone senses when you tilt it. But digital screens can and do fail. If the magnetometer fails, you lose your heading information and bam, a giant red X appears right where your heading number should be. And if the entire AHRS goes down, the primary flight display background goes completely black, an AHRS fail alert pops up, and you're staring at red X's across all your indicators. When that happens, you have to transition immediately to your standby round gauges, and that, my friends, is exactly why we need to thoroughly understand our backup mechanical systems. Moving right along to part two, the vacuum system.
Think of this system as the mechanical heart of our backup instruments. And as with everything in aviation, we've got redundancy. We actually have two pumps. First, there's the primary engine-driven vacuum pump right up there in the engine compartment. But moving back toward the baggage compartment, we have a backup auxiliary electric pump. So if that main engine-driven pump decides to quit on you, you just manually flip on the electric one. Just keep in mind that auxiliary pump is strictly for standby. You should never ever take off if the primary pump is already inoperative.
So how does this whole thing actually work? Well, it's all about creating low pressure. Step one, the pump creates a vacuum, which essentially pulls air into the system. Step two, that air gets pulled cleanly through a filter. Next, it passes through a vacuum regulator, and that's just there to make sure the pressure stays properly managed, even when your engine RPMs are fluctuating all over the place. Finally, this steady stream of air physically hits these tiny cups positioned around the gyros inside your instruments, and that forces them to spin at unbelievably high speeds. Now, I need you to burn this specific number range into your brain, 4.8 to 5.1 inches of mercury. That is the absolute optimal suction range you want to see on your vacuum gauge. If it's too low, the gyros just won't spin fast enough, meaning your instrument readings will be totally unreliable. But if it's too high, that excessive force can actually physically damage the gyros. Thankfully, a pressure sensing switch is always keeping an eye on this, and it'll trigger a vacue warning light if the pressure drops too low.
All right, part three, gyroscopic physics.
To truly understand how these spinning chunks of metal actually become useful flight instruments, we have to look at our first principle, which is called rigidity in space. Simply put, a spinning disk heavily resists external movement. It actively wants to stay spinning in its exact original plane of rotation. And that is huge, because it gives the aircraft a fixed, rigid reference point against a constantly rotating Earth and, of course, the pitching and rolling of the airplane itself. A really fantastic way to visualize this is just to think about a spinning bicycle wheel. If you've ever tried riding a bike with no hands, you know it's incredibly wobbly when you're going slow. But as you pedal faster and that wheel really gets up to speed, it suddenly becomes amazingly stable, right? The wheel wants to resist tilting. Well, an aircraft gyroscope does the exact same thing, but we're talking thousands of revolutions per minute. Then we have our second principle, gyroscopic precession. This one is wild. It dictates that any force applied to a spinning gyro will actually be felt exactly 90 degrees later in the direction of rotation. So let's go back to riding that bicycle with no hands. If you lean to the left, you're basically applying a force at the top of the tire. But because the tire is spinning forward, clockwise, that force is actually felt 90 degrees later at the front of the tire. That effectively pushes the tire left, which is exactly how you can turn a bike just by leaning. Which brings us to part four, the flight instruments themselves. So let's apply these physics principles directly to the gauges sitting right in front of you. Take the attitude indicator. Inside that instrument, the gyro spins horizontally around a vertical axis. And thanks to that rigidity in space we just talked about, the gyro stays perfectly parallel to the Earth's surface. It connects to the display face through some mechanical gimbals. So as your airplane pitches and banks, the plane is quite literally rotating around that fixed internal gyro. That's what causes the little miniature aircraft on your display to move relative to the artificial horizon bar. But wait, what happens if you pitch up more than 70 degrees or roll way past 110 degrees? Well, the instrument can physically tumble. The gyro hits its internal limits and completely loses that rigidity. To fix this, the attitude indicator has this truly brilliant self-erecting mechanism called pendulous vanes. They use these tiny jets of leaking vacuum air. So when the gyro isn't completely level, these vanes open up to shoot air out. This applies a tiny force that uses, you guessed it, gyroscopic precession to gently push the gyro back so it's parallel to the horizon. Next up is the heading indicator, and this one spins vertically around a lateral axis. Now, unlike the attitude indicator, this guy does not have pendulous vanes. Because of the precession caused by internal friction, plus the fun fact that the Earth is rotating beneath you at 15 degrees an hour, the heading indicator actually creeps over time. It'll drift about 3 degrees every 15 minutes. Because of that, whenever you're in unaccelerated straight and level flight, you absolutely have to constantly manually align it to your magnetic compass. And remember, aviation is all about safety through redundancy. You'll notice that your attitude and heading indicators are driven by that pneumatic vacuum system. But your turn coordinator, the one that shows your initial roll rate and standard rate of turn, well, it has its very own gyro spun by a totally separate electric motor. So if your vacuum pump completely fails on you, that electrically driven turn coordinator is going to keep right on spinning, making sure you still have a reliable way to keep the aircraft oriented. Let's move into part 5, compass errors. Okay, so if you lose your heading indicator entirely, you have to look to the ultimate backup, which is the magnetic compass. But to really master the compass and understand its, let's say, unique physical quirks, you need to memorize this acronym, VDMONA. That stands for variation, deviation, magnetic dip, oscillation, northerly/southerly turning errors, and acceleration errors. These are the sneaky little quirks that will absolutely trick you if you aren't paying close attention. Let's break down the most critical ones. First up is variation. Look, the Earth is a giant magnet, right? But the geographic true North Pole is not in the exact same spot as the magnetic North Pole. Your compass points to magnetic north. That angle of difference between the two, that's called variation. To correct for this when you're flight planning, we use a super simple rhyme. East is least, so subtract. West is best, so add. And it's probably worth noting deviation here too. That's a compass error caused by local magnetic interference right inside your own aircraft's electrical systems. Seriously, even placing your iPhone too close to the compass can cause deviation. Now, because the Earth's magnetic lines of flux physically dip down into the Earth at the poles, the compass card actually wants to dip down too. To counteract this magnetic dip, manufacturers install a tiny counterweight on the compass float. But fixing one problem creates another. That weight causes 2 major turning errors in the Northern Hemisphere. We remember them with the acronyms UNOS and ANS. ANS means if you're on an east or west heading and you accelerate, the compass will falsely swing north. If you decelerate, it swings south. UNO stands for undershoot north, overshoot south. Let's actually visualize what that means. So, applying the UNOS rule, if you're starting a turn from a northerly heading, the compass is actually going to initially swing in the completely opposite direction, and then it'll lag behind your actual turn. Because it's lagging, you have to roll out of your turn early, meaning you undershoot north. Conversely, if you're starting a turn from a southerly heading, the compass actually leads the turn. It spins faster than you're actually turning. Because of that, you have to intentionally turn past your desired heading before rolling out, so you overshoot south.
All right, bringing it all together with part 6, time turns.
So picture this, your heading indicator just failed and your magnetic compass is bouncing all over the place because of those via-dima errors during a turn. How on earth do you accurately fly a precise heading while stuck in the clouds? The answer is time turns. By using your electrical turn coordinator, you establish what's called a standard rate turn. In a standard rate turn, the aircraft is turning exactly 3 degrees every single second. That means a full 360-degree circle will take you exactly 2 minutes. So let's just do some quick math. If you need to turn 120 degrees, you divide 120 by 3, which gets you 40 seconds. You just have to start your timer the exact millisecond you begin that turn. Trust the clock. The moment that clock hits exactly 40 seconds, you execute a standard rollout and boom, you will be perfectly lined up on your new heading. So, we've covered everything from modern digital screens and the mechanical heart of vacuum systems to the wild physics of gyroscopes and the sneaky mechanical quirks of the magnetic compass. Look, when those fancy glass screens inevitably go dark on you, true safety is built entirely on redundancy and your foundational knowledge as a pilot. So I'll leave you with this. Are you fully prepared to trust the invisible physics spinning away just behind your dashboard? Study these systems, deeply respect the mechanics, and I promise you, you'll always find your way safely through the clouds. Thanks so much for joining me for today's explainer. Keep learning, keep practicing, and fly safe.